My name is Bob Janda. I am a physicist with 30 years experience in color technology. We are going to learn about color today. The presentation is designed not around how pretty colors are, such as my tie, but more industrial color. We have, for example, this color standard used by a major raisin company in California, where they want all their packaging to be this ideal color. However, they are willing to accept a color that is off color by this much. So what we're able to do is to measure this color, determine what the color differences are, and as long as the packaging is within that range, they will accept it as packaging. Another one of our customers is Hershey. This is the ideal packaging color for their candy bar wrappers, but they will accept this surround color. So this is an acceptable industrial packaging color. We are going to learn about color. We're going to judge color. We're going to measure color. And we're also going to look at the tolerances used in industry for setting in the tolerances around a particular color standard. As an example, we can take a spectrophotometer, place it on a color standard, take a picture of it, and what comes up in the spectrophotometer is what's known as LAB coordinates. Now, let's learn about color. To give you a background, this slide shows the electromagnetic spectrum and how it relates to our world. On the left, we have X-ray wavelengths. On the right, we have AM radio wavelengths. And in the middle, we have the visible spectrum. The visible spectrum has a range of 340 to 780 nanometers. This is where we see color. I ask you, how many colors can you see? Some people have said 4, some say 1,000. It turns out the average person can see about 13 million colors. A colorist, who is a person who specializes in color analysis, sees much better than the average person because he has developed the ability to analyze how much red, how much blue, how much yellow, and how much green is in the color he is viewing. He sees much better than the average population and sees about 80 million colors. It takes about 2 years to develop this skill set. Color is obvious. If we are producing a product and have a good quality control of our color, the consumer assumes that the overall product is good. Off-color products implies poor quality. As an example, if you're going to buy a candy bar and you see 2 candy bars on the rack, one candy bar is lighter in color, you're thinking to yourself, well, that's been sitting there a long time and it is faded, so I'm not going to buy that one. In reality, the package may have been printed off color. Most people are looking at products, and if the product matches in color, the person says to himself, hey, if they can't get the color right, what else don't they get right? Some examples of items under tight color control are listed here, and they include items like the color of McDonald's hamburger buns and even the color of Purdue chickens. It's incredible, but Purdue is able to adjust the yellowness of the chicken skin to meet the color desired by the consumer. They adjust the amount of marigold seeds in the chicken feedlot. By then overdosing with a higher amount of marigold seeds, the concentration then turns the skin of the chicken yellow. The consumer thinks he is getting a fat, healthy chicken. Well, Purdue chickens are healthy, but they're not fat. They just have a yellow skin. This shows a light source being reflected off of a color chip. If you put your eye where the specular reflection is coming off at, that's where the white arrow is, you will see 98% of the reflected light coming in from the light source. This is all white light. Color comes off in all other directions. Color can be evaluated visually or by instruments. The ultimate judge, of course, is visual. Instruments serve a useful purpose to communicate color. When you do visual judgment, this needs to be done under controlled conditions. Color judgment in industry usually complies with an ASTM specification. ASTM stands for the American Society of Testing Materials. They have established how to view color visually. They specify using 3 light sources with 100-foot candles of light. You place the standard and the sample color adjacent to each other, and you view at a 45-degree angle. Oh, and by the way, they also say the person should not be colorblind. If you are colorblind, you probably don't know it. This shows a quick test for color blindness. The top left ball has a number 63 and the lower right ball has a number 32. If you don't see these numbers, you may need to have your eyes tested for color blindness. Color technology uses a color notation called LAB. This takes into account the illuminant, the object, and how the eye sees color. This is complicated, but basically we take the spectral curve of the illuminant, we mathematically multiply it by the spectral curve of the object, then multiply that by the spectral curve of the eye, and believe it or not, we come up with a color coordinate known as LAB. LAB is a color space system used to communicate color. It is a 3-dimensional Cartesian coordinate system. The L-axis goes from the bottom, which is black, to white. The bottom is black and assigned a value of 0. Pure white is at the top of the L-axis and assigned a value of 100. There is an A-axis with a positive value of A that goes to the red, and a negative value of A goes to the green. It also has a B-axis with a positive value of B going yellow and a negative value of B as blue. This is a convenient method of communicating color. As an example, if I say my LAB color values are L equal 50, A equal 50, and B equal 50, if you go to the graph, go up 50 units on the L-axis, go out to the right on the A-axis 50 units, and go back 50 units on the B-axis, we now have a point in color space which is orange. Typically, we use 3 illuminants. Daylight is called D65. The D65 stands for light radiation coming from a black body at 6,500 degrees Kelvin and simulates daylight. There is an A illuminant, which is an incandescent light bulb. Looking at the spectral curve, it has a lot of red. We also have a fluorescent illuminant, which is typically bathroom light. Each one of these typical lighting conditions occur in our daily life. We measure an object using a spectrophotometer to characterize the spectral reflectance of our product. The human eye has a spectral response as shown here. Let's measure some color. There are 2 basic instruments used in color measurement. One is called spherical geometry, and the other is 45-0 geometry. The sphere geometry measures color only, and the 45-0 geometry measures appearance. The sphere geometry is used for color formulation and reads only pure color. It is called specular component or SCI mode. The sphere is like a tennis ball with a white coating on the inside of the ball. We flash a light on one side of the ball, light bounces around on the inside of the ball and ends up omnidirectionally onto the sample we want to read, which is our red sample at the bottom. We read the reflected light off of this bottom sample at 8 degrees off the normal axis or off the straight down direction. A second instrument is called 45-0 geometry. In this case, we light the product at a 45-degree angle and we read the reflected color normally or on the straight down direction. This measurement is called SCE, or specular component excluded, and it reads appearance. This is the way the eye sees color. Appearance includes pure color and the effect from gloss and the effect of texture on the sample. In color technology, we use both instruments. As an example, if you are a textile dyer, you would want to use a sphere instrument to get your fabric on color. And once the dye bath is on color, you would then want to read your product with a 45-0 instrument, which would include all of the other factors such as gloss and texture as to the way the consumer sees the fabric. Please note, spherical geometry has an optical port that can be adjusted to read both color and appearance. Thereby, you need to only use a single instrument. With color differences, the eye can see one shade. Color measurement instruments, however, see 10 times better than the eye. Color differences can be calculated between a standard and a sample product. We can measure a standard with its LAB value, then measure the sample with its LAB value, then we take the difference between these two, and that is the color difference in each one of the color axes. The color difference between a sample and a standard can be calculated to come up with a handy color difference known as a delta E. In this case, we have a delta E of 5.15, or it's about 5 shades between the two samples. The delta E is the amount of color difference between your standard and a sample as calculated by the Pythagorean theorem. This is the equation you learned in high school, but you may not remember it. The delta E carries a notation with it such as CMC. This is a color tolerancing system that follows how the eye sees color difference. A value 1 in delta E, CMC, is 1 shade color difference no matter where you are in color space. This allows a person to communicate color differences around the world with regard to shade differences as seen by the human eye. Typical delta E values are shown here, and they vary based upon industry. If we have 2 steel chainsaw housings that snap together, you want a delta E of 1. Pringles food packaging uses a delta E of 3. Armstrong tile flooring use a delta E of 0.4. The shirt to yoke difference at the Gap on their shirts has a delta E of 1. The Mercedes trunk to quarter panel has a delta E of 0.5. Generally speaking, the closer the color match in delta E, the more expensive the product. This concludes our presentation, and hope you have learned a little bit about color.